Okay, so your do now was to draw two isomers for C4H5N. And there are more than two, but you only need to draw two on the quiz. When I grade your quiz, I look for certain things. Does carbon have 4 bonds? Is hydrogen always a terminal atom? Does nitrogen or phosphorus have 3 bonds, 1 lone pair? So these are things I'm looking for. And these are possible isomers shown here. And you can check your work now and see if you have any of these isomers. And if you don't, that's okay. You may have another one. I didn't necessarily draw every single one. So in the first one, again, N wants 3 bonds, like phosphorus, group 15, 8 minus 5 valence electrons is 3. N wants 3 bonds, which it has 1 lone pair to complete the octet. So I did a double and a single here. This carbon has an octet of electrons, 4 bonds, as does this, as does this, as does this. So this is one possible structural formula. Now when you go to draw an isomer, think about changing one piece right away. Remember that a mirror image is not an isomer, so don't just flip it over or flip it on its back. Change something up. So instead of the double and the single, I was thinking triple lone pair. Again, nitrogen and phosphorus, 3 bonds, 1 lone pair. Each carbon has an octet, and that's another possibility. Also make sure you count that you have 5 hydrogens. That's another thing I'm going to be looking for. Here's another possibility here. Again, I have a triple bond. Actually, this looks the same. I think one of the kids asked me if this was okay in the other period. This is the same. And then this looks the same too. So it's just these two. I think I drew it 5th hour and then I drew it 6th hour. So I just did it side by side.
That one's different.
What's different?
The last one has 3 H's to 1 C, and then the other ones only have 2 H's.
No, but see, 3, 3, this is this, and this is this. So I think what happened, yeah, I think I did it 5th hour, and then the kid 6th hour said, oh, can you draw it? So we drew it slowly, and that must have been 6th hour's answer. So here's 2. Do you have something else?
Yeah, I had, like basically the last one you have, or the first one, the same thing. But I had the N with the triple bond, and then I had, like...
Let me see. Because there are other ones you could have done. Instead of going double, double, you probably could have done triple here and made it work. We can try that, but maybe that's what you have. Which one?
This one.
This one? Yep, this one's different, so that works. So he had the triple here, and a double here, and a single here. Each carbon has 4, so this is perfectly legit. So there are many options that you can draw. Just make sure carbon has 4 bonds, nitrogen and phosphorus 3 bonds, 1 lone pair. And hopefully you spent some time drawing all of the structures in number 2 on your classwork. And how do you feel about your drawing at this point? You've got it? All right? So watch for this on the quiz. Carbon forms 4 bonds. Don't put lone pairs on carbon. It's very rare that it occurs. It occurs with carbon monoxide and cyanide ion, and I won't give you either of those. Make sure nitrogen and phosphorus, 2 bonds. I'm sorry, 3 bonds, 1 lone pair. And one of the kids was asking about this in the other class, so I sort of scribbled it out for them. I don't know if that'll be helpful to you. Halogens like fluorine, chlorine, bromine, iodine, single bond, 3 lone pairs. Hydrogen, just 1 single bond. Oxygen and sulfur in group 16, 2 bonds, 2 lone pairs. So either 2 singles and 2 lone pairs, or a double at the end, making it a terminal atom, and 2 lone pairs. And the nitrogen we just saw, phosphorus would be similar to nitrogen. So you could do this. I don't know this structure would have worked, we could try it. If we had gone, I'll scroll it back down in a sec. If we had done C, 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 N, and if we had gone all singly, no, if we had gone singly with the N, so N has all single bonds, we still have 3 H's to place. I'm not sure we could get there. Yep, you can, right here. So that's a good way to go about with your isomers. And you can work from one end to the other. Just look at the bonds. Like I said, I'm going to make sure carbon always has 4 bonds, nitrogen and phosphorus 3, and a lone pair. Oxygen 2 bonds, 2 lone pairs. And I'll slide that back here in case some of you were grabbing that. I can give you that other structure too. Question? I answered it? Okay. All right. So you see when I draw compounds, sometimes I fly the hydrogens at certain angles. There's actually a reason for that. And when you construct these compounds with molecular model kits, you'll get a much greater appreciation for the shapes that the compounds can form. And that's what we're going to start with today, is shape or molecular geometry. It's very, very, very easy. The kids are always really good at it. At first you're going to be like, oh, there's bonds everywhere, there are lone pairs. We're going to keep it very simple. We're going to go over each shape. I've constructed the shapes to show you what they look like. And then I'll draw a big, big molecule, and you'll see that you can identify the shapes. And you're going to get a lot of practice in the lab today with this concept. No. Your quiz is Friday. Your test is Tuesday. But once you do the lab, you'll feel a lot better. The lab also gets into polarity, which we will cover as well, but you have to understand shape before polarity. Okay, so for those of you who are going to be out Tuesday, I'll talk to you separately. If you're still going to be here Monday, you may want to take it before you go. This way it won't sit all vacation. And then you also have your project due after vacation. So I don't want you to have a lot of work to do over vacation. I may push the project back slightly, but I don't want you guys to procrastinate. All right, so this all fits into our overarching learning goal that we've talked about quite a bit. We're going to be into the shape and the polarity today. So in your notes, I'm going to flip screens. Did I show you how to draw the polyatomics? Yeah. Good. All right, so shape and polarity. So we have a short lesson today, and then the whole second half of class, and probably more, will focus on the lab, which is very fun. You'll enjoy it. The kids like playing with the molecular model kits. It's fun. It's like Tinker Toys. Okay, both shape, known as geometry, but not like geometry you did in math with theorems and stuff, and polarity are very, very important for knowing how the compound's going to react, as well as its chemical and physical properties. Chemical being its reaction, physical its appearance, basic properties where you don't have to alter the substance. The whole basis for determining shape is based on a theory known as VSEPR, for valence shell electron pair repulsion, and this allows you to predict the shape, and you can do that if you know how many atoms are bonded directly to the central atom. I'll show you what I mean. And how many lone pairs are on the central atom, not a terminal, but the central atom. So your focus is on how many atoms bond directly to the central atom and how many lone pairs are on the central atom. You'll see that the electron pairs will orient themselves as far apart as possible in an effort to minimize repulsion. electrons are negative, so you have two electrons in a pair and they will repel one another, and then those pairs will repel other pairs. So it's like three kids who don't get along, you're not going to sit them really close to one another because they're going to fight. You're going to sit them at opposite ends of the classroom. Same concept. When you want to draw the structure and determine its shape, you're going to draw it as we did previously. So you draw your structure, and then you can use this chart to determine what the geometry is relative to the central atom. If there's more than one central atom in the structure, there's more than one geometry, and you'll report it as such. We have 5 shapes here: linear, bent, trigonal planar, and the hardest thing about this is the pronunciation, tetrahedral, trigonal pyramidal, tri for 3, tetra for 4, as we discussed the other day. We're going to look at how many atoms are bonded directly to the central atom. We're going to look at how many lone pairs are on the central atom, the bond angle, and finally examples. And we're going to work it backward. I'm going to draw the examples for you, show you what they look like with kids, and then you'll see how we determine the shape. I have included this chart here just to give you an idea on the bond angles, and we'll point this out as we draw. So the first shape that we're going to look at is linear. Before we even look at the different shapes based on the chart, I do want to make one thing clear, because some of the kids were confused about this because they said, oh, but that doesn't work on the chart. But you know this already. If I had 2 points and I connect them, what do I get? Starts with an L, a line. So if you only have 2 atoms, the shape has to be linear. So if you have hydrogen gas, it's linear. If you have chlorine gas, it's linear. If you have oxygen gas, it's linear. And I position my electrons this way. You can just have the pairs separate because that will minimize the repulsion. But if you only have 2 atoms, it must be linear. Okay? So let's focus a little bit more on the linear shape when you have more than 2 atoms. For example, we looked at carbon dioxide previously. Carbon dioxide, you have a carbon bonded to 2 oxygen atoms. These 3 atoms are in a straight line. You can see that here, the atoms are in a straight line, and we say that the shape is linear, and the bond angle here, as if you had supplementary angles, is 180 degrees. Anytime you have a triple bond, you've got to have a linear central atom. The way I like to go about shape determination is I look at the central atom, and now you want to look at the screen. This carbon is directly attached to 2 atoms, so I'm writing 2. That tells me how many atoms the carbon is directly attached to, and there are no lone pairs on the central atom carbon. So if you have 2 atoms attached and no lone pairs, the shape is linear. Bond angle 180. First shape. The bent or angular shape comes in two varieties with different bond angles. You can have sulfur dioxide, and this has a little bit of a funky structure. I wouldn't give you this one, but it's a good example. This is one of the few times you'll see where oxygen will form a single bond, 3 lone pairs, and sulfur can do this, but usually sulfur acts like oxygen. So I won't give you this one to draw. For your purposes, follow the rules we talked about. Oxygen and sulfur like 2 bonds, 2 lone pairs. This sulfur is attached to how many atoms? 2. And how many lone pairs on the sulfur? 1. A 2-1 combination is bent. This bond angle is about 118 degrees. I did not ask you bond angles on the quiz. I don't really think I asked you it on the test. I'll double check that. I'd expect you'd know 180 and the 120 I'm going to show you. The other ones are trickier. The other type of bent design that you'll see more frequently, for example, is water, where the oxygen is bonded to 2 hydrogen, directly bonded to 2 atoms. And how many lone pairs on the oxygen? 2. So this is bent also, although this is 104.5 degrees. So it's a tighter angle than that one, for reasons that are really too advanced to get into. So you have linear and bent. Linear, 2 atoms attached, no lone pairs. Bent, 2 atoms attached, either 1 or 2 lone pairs. And you can see a water molecule, and you'll be constructing one as well, and that's a water molecule. So one advantage of these molecular model kits is you can clearly see bond angles. A disadvantage is you can't see the lone pairs, although you know they exist, because if they didn't, it would be linear. The next shape is trigonal planar. Tri means 3. 3 atoms attached. For example, boron trifluoride. Boron is very interesting because boron does not have an octet. It forms 3 bonds, no lone pairs. We don't do that much compound drawing with it, but it does come up in the shape and polarity section. So boron has an incomplete octet. It has a sextet, if you will, 6, or a hexatet. I think you'd say sextet.
Yes.
If you had 5 babies, it would be sextuplets?
You had 6 babies.
6 babies. What did I say, 5?
Yeah.
No, 5 would be quin.
Yeah, quintuple.
So what would 6, I guess, would be sextuplets. Oh, that would be crazy. Who would want 6 babies at the same time? Well, she's crazy. All right, but I shouldn't state my opinion. Nuts. All right. It's hard enough to have one at a time. 3 atoms attached, no lone pairs. Bond angle, 120 degrees. I don't have that one constructed, but I do have this trigonal planar. And what you'll find Is it on the screen? All the atoms are in the same plane, and you can see right here that the bond angle is about 120. You'll see that it's larger if you line these up. I'm going to hold them up. This is tricky to do because then they fall apart. Get in there. So when you line, I got to get my fingers out. Crazy. All right, I'm doing the best I can here, but I guess my fingers are too sloppy today. My compound fell apart. Maybe I can put that one down and that one on top of it. That might be easier. Not exactly. Oh well, I tried. But I think it got squeezed a little bit with this one. Probably changed it slightly, yeah. When you play with the molecular model kits, it's a little bit tricky. Make sure you just gently screw the balls on and off, because if you ram them on and off, you're going to bend the springs, and then they don't bend back. So like here's a bent little spring from earlier. So just be careful with them. All right, trigonal planar. And we're going to put all the shapes together in one molecule, and you'll see that it really is very simplistic. All right, fourth shape, tetrahedral. From tetra, what would you guess in terms of the number of atoms attached? 4. And an example is methane. And when you draw methane flat, it looks like the bond angles are 90 degrees, but they're not. If you actually drew it, you'd find this bond angle is 109.5 degrees. This hydrogen's going to come out at you, and this one goes into the paper, and it would be drawn this way. So you can see if that's the angle that's coming towards you, that's away from you. And this angle is about 109.5. Tetrahedral. Again, 4 atoms attached, no lone pairs on the central atom. That's where kids get confused. You're looking at lone pairs on the central atom. And then the last shape is trigonal pyramidal. Scoot. So the last shape is trigonal pyramidal. For example, ammonia, 3 atoms attached, 1 lone pair. So 3 attached was your trigonal, and then the lone pair pushes the other atoms closer together, and you get a pyramid shape. And not drawn to scale here, but the bond angle is about 107 degrees. But that's very nitpicky. So I know it seems overwhelming, but I'm going to draw a very big structure, and I think you'll see that you can identify every single shape using the chart. Today during the lab, you're going to use the chart. On your classwork in number 2, you should have drawn all the structures already. If you didn't, you're not prepared today, so that's not so good. Once you've drawn all of them, you can determine every single geometry with respect to a central atom, and that'll be very good practice for you. Because on the quiz, you're going to draw 4 structures and identify 4 different shapes. They don't all have to be on the same structure, but I'll give you one here, for example. Of course. Oh, you have a pass. Go ahead. Now structure good? That's how you're going to check yours. Hydrogen, nitrogen 3 bonds, lone pair, carbon with 4, carbon with 4, carbon with 4, halogen 1 bond, 3 lone pairs, carbon with 4, carbon with 4, looks good. So, this is just any generic structure, but let's take a look at every single central atom now, and let's see if we can identify the shapes. Ready? This N, here's my approach, I'll help you with the first, is directly attached to 1, 2, 3 atoms, has a lone pair on it. So a 3-1 is what? Trigonal, pyramidal. Okay, how do we do this one? Directly attached to 1, 2, no lone pairs. That's linear. What's that one? Same thing. How about that carbon? Directly attached to 1, 2, 3. How many lone pairs on the carbon? None. So that's a 3-0. Trigonal. Planar. So it's this one also? This one too? Yeah, so all of these. And then how about this O? 1, 2 things attached. How many lone pairs? So that's bent. Yes, yes? It's not hard. You're going to be good at it. What? Yep. You're going to do a ton of shapes today. The only place I find kids mess up is the lone pairs have to be on the central atom to affect shape, not on a terminal. You don't do shapes of terminal atoms. They're just at the end. And in your lab today, you're going to do shape, 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 and you'll be very, very, very good at it.
Is this it?
We have one more piece. We have polarity. Do you want me to give you another one of these to do? Or you got this? What do you want? What do you want? You're good? You're going to get a ton of practice with it in the lab and on your classwork too. So which shape did I not do? I didn't do tetrahedral and I didn't do the other bent. So let's do a little structure actually because I just want to make sure you have everything. We'll keep this one simple. This one, this one, this one. And when you identify 4 different geometries on your quiz, they don't all have to be on the same structure. Some can be on the same structure, they can be on different structures, just have to be different. So what would this one be? Tetrahedral. 4 things attached, no lone pairs. How about this C? Trigonal planar, 3 things attached, no lone pairs. And what about this one? Be careful. The N is attached to how many atoms? 2. How many lone pairs? So that's bent. That's the one kids sometimes mess up. That's why I wanted to give you that little structure. All right? And then the last thing we want to talk about today is polarity. Polarity is not on your quiz. It is on your test. It is on the lab. And this is a very short lesson, but you have to understand shape to do polarity. So we're going to go through polarity, which is right here in your notes. And then we're going to use both of these concepts as well as drawing structural formulas and constructing them in the lab, and that'll be really good practice for you, and we should have a good 55 minutes to do the lab today, and you'll get most of it done. Any carryover we'll finish next time. All right, we talked about bond polarity already. This was at the beginning of the lesson, and we said, for example, with covalent bonds, the bond can be nonpolar covalent or polar covalent. So this is just a review of what we did previously. A C to H bond, we can get the electronegativities of these elements from the back of the periodic table, just like you did in number 1 in your classwork. If you subtract the 2, you get 0.3. 0.3 is less than 0.5, so the bond is nonpolar covalent. In contrast, if you had a C to O bond, electronegativity of carbon is 2.5, oxygen is 3.4, the difference is 0.9, and that is between 0.5 and 2.1. So this bond is polar covalent. So we're going to look at the polarity of the compound using bond polarity as well as shape. And that's what we're going to look at here. I have to flip back, hang on. And the bond polarity stuff, you already have it in your notes. That would have been from our very first lesson in this chapter. Okay. All right. So it says if the molecule contains more than 2 atoms, the molecule's polarity or the molecular polarity depends on the bond polarity as well as the shape of the molecule. So we've got to look at both criteria. We've got 4 different scenarios here. I'm going to draw examples of each one. In A, it says if all the bonds are nonpolar and there are no lone pairs of electrons on the central atom, the molecule is nonpolar. So we're going to look at these different scenarios here. This is A. So the first one says if all the bonds are nonpolar and there are no lone pairs on the central atom, you're going to have a nonpolar molecule. For example, methane. We showed previously that C to H bonds are nonpolar. So we have all nonpolar covalent bonds, and we have no lone pairs on the central atom. And with this combination, the molecule is nonpolar covalent. So when you look at your structures, you're going to look at the bonds. If they're all nonpolar and there are no lone pairs on the central atom, the molecule is nonpolar covalent. Now, if you only have two of the same atom, it has to be nonpolar covalent because the electronegativity difference would be 0. B says if only one bond is polar, the molecule is polar. For example, methyl fluoride. Is a C to H bond polar or nonpolar covalent? We just looked at it. Is a C to H bond polar or nonpolar? Nonpolar. So nonpolar, nonpolar, nonpolar. Now a C to F bond. Any nonmetal that hooks with fluorine is going to be polar, but you can test it. Electronegativity of 2.5, electronegativity of 4. Again, these values can be found on the back of your periodic table. The difference here is 1.5. When the difference is between 0.5 and 2.1, like number 1 in your classwork, is it a polar or nonpolar covalent bond? Polar. So this bond is polar. Now we talked briefly about dipoles. Remember, the more electronegative atom pulls the bonding electrons toward it. So which atom would have the partial negative, the carbon or the fluorine? Fluorine. So fluorine has the partial negative, carbon the partial positive. So you have a dipole right here. So you have 3 nonpolar bonds and 1 polar bond. So the molecule is polar or nonpolar? Polar. Go ahead.
What if you have a molecule that is it can be an isomer, and in one way of drawing it, it's going to be nonpolar, but in the other way, it will be a polar molecule?
I can't think of an example where that can happen. I would say, I don't think so. I think if you've got an isomer, it's going to be consistent. It may not be as polar as it was because the dipoles can add up or start to cancel each other slightly, but I think once you're polar, you're polar. But that's a really good question. I'd have to think hard. I can't think of an example, so it's a very good question. All right, C. It says the presence of a single lone pair of electrons on the central atom results in a polar molecule. Bench structures also illustrate polar molecules. For example, and I'll give you 2, ammonia and water. I will tell you that an N to H bond, and you can test it, is polar covalent. But it doesn't even matter. The presence of a lone pair, or if you have a bench structure, makes for a polar covalent molecule. So if you ever have trigonal pyramidal or bent, you're going to have a polar covalent molecule. So if you ever see that shape in your lab, your molecule will be polar covalent. So you know you have polar covalent if one bond only is polar, or if you have a lone pair or a bent structure. Now be careful with the statement that, oh, if you ever have lone pairs on a central atom, it's polar, because that's not always true. But trigonal, pyramidal, and bent will always be polar. The last rule is the trickiest. It says, if the bonds are polar, examine the symmetry. If the molecule is perfectly symmetrical, it can bend back on itself, has no lone pairs on the central atom, and all atoms bonded to the central atom are the same or have similar electronegativities, the molecule is nonpolar because the dipoles cancel. For example, carbon tetrafluoride is a perfectly symmetrical molecule. If you folded this here, it would fold right back on itself. If you folded it here, it would fold right back on itself. Are there lone pairs on the central atom? No. I already told you that any nonmetal hooking to fluorine will be polar covalent in terms of the bond. So the bond is polar covalent. This is like a child throwing an absolute temper tantrum somewhere, and he's spread eagle with his arms this way and his legs out, and 4 adults come and try and pull him at the same time. The kid's not going anywhere because the poles are all equal but opposite. If there's a bag of candy in the middle of 4 people and they're all trying to reach for it at the same time, it's not going to go anywhere. So these dipoles are equal but opposite. They all have the same pull in opposite directions, and so they cancel. So this molecule, even though it has polar covalent bonds, the molecule is nonpolar covalent because it is symmetrical and the dipoles cancel. And the examples I've given you are predominantly the ones you would see. You won't have to explain this out at this level. You'd see it in a multiple choice question with probably grossly similar examples. This molecule is nonpolar because the dipoles cancel due to the molecule being perfectly symmetrical. Okay? And you're going to see polarity. Once you have one polar bond, as long as you don't have symmetry, the molecule is polar. And this is assessed in your lab. Okay? We will hit intermolecular forces after the quiz. They really want us to teach this at the honors level. I think it's very, very tricky. I'm going to teach it to you in a manner that I'm sure you will understand, and I'll show you exactly what might be addressed. We are going to shift gears now, as long as there are no questions. Questions? You're good? All right, and you're going to put everything that we did today to good use in the lab. I need about 3 minutes to explain the lab, and then you'll be ready to play in the lab, and it's really very fun. With your lab today, you're going to read the introduction. Read it. There's information there that you need to answer the questions with. Our objectives are to draw Lewis dot structures, to construct them, which will help us understand the shape better. By looking at the shape and bond polarity, we can determine the molecular polarity. So a lot of objectives that we've been talking about in class. I will give you a ball and stick model set with your molecular model kits, some of the kids left them at the bench top. Just make sure that you take the one that goes with your group. You're going to be picking up 2 kits. So if you're group 7, you get 2 kits that are rubber banded together. In these molecular model kits, you will find a key that tells you what color represents what atom. So black represents carbon, blue could be nitrogen or phosphorus. So if it's in the same group, the color will be the same. Yellow is hydrogen, etc. So this will be your key. You'll need both kits to construct the compounds, especially if you want to leave some of them together to do your analysis. Please be careful with the springs, as I mentioned earlier. Just twist them in gently, untwist them gently. When you ram and pull is when they break. These molecular model kits belong to me. They don't belong to the school. Please be careful. The balls will roll off the table with ease, so they bounce everywhere. Try not to lose any. This is a good class. I'm not worried. I'm going to show you how to do the first set, and then you'll be ready to rock and roll. You're going to be filling out the following table. I highly recommend pencil. The Lewis dot structure will show the atoms side by side with the shared pair between them. The structural formula will show H bonded to H through a single bond, a stick to represent the shared pair. Now, I don't care if you do this Lewis dot structure column. Some of you are able to go directly to the structural formula, and that's fine with me. So as long as it's right, you get credit for both. If you ever only have 2 atoms, what's the shape? Linear. And if you have 2 of the same atoms, the molecule has to be nonpolar covalent because the bond doesn't have polarity, so the molecule doesn't either. And then you'll construct it. My molecular model kit's different. The white is hydrogen. I'm not sure why. But it would just look like this. And you can see linear. So that's where it's a huge advantage with the molecular model kits, because you can see the shapes very clearly. Okay? You'll work through the rest. Again, pencil, pencil, pencil. I know you can get all of these drawn shapes and polarity today. Some of you will probably answer some of the questions. Next time we will quiz. We will have our lesson on intermolecular forces. The second half of class will be to complete the lab and address anything necessary for the test. I do want to mention that this test, well, predominantly Chapter 6, does have naming and formula writing of ionic compounds in it, as well as a few oxidation number questions. So if you didn't master that previously, you want to make sure that you have at this point. Several of you did extremely well on the last test, so you did show mastery in those areas. I will post on Edline another class worksheet that has naming and formula writing of ionic and covalent all mixed together. That's when it gets tricky. You have to remember with ionic compounds, a metal and a nonmetal, or polyatomics. With covalent compounds, 2 nonmetals with the naming and formula writing, and that will help you differentiate and get you ready for your test. Your quiz is only on Chapter 6 through shape. All right? What you'll want to do is pick up a molecular model kit as well as 1 packet for the group. So for example, group 7 is all set. Just send 1 person over to get the kits. You can leave the kits at your bench top today. Period 5 will be continuing with their lab today. Other than that, I think you're ready to go. I think this will be tremendously helpful to you. If there's someone in your group not understanding completely, please explain it to them.